we present harmonic networks for deep translation and rotation equivariance. Take this tiger. If we rotate it, how would its deep feature representation transform? It's difficult to predict. This is a common criticism of convolutional neural networks. They are black boxes relying on hard-to-interpret internal processing. Visualizations help a great deal in understanding the features learned, but they take time to produce and only give a glimpse into the complicated laws which govern deep feature spaces. One of the simplest laws of deep feature spaces is translation equivariance. If we translate an input image to a CNN, then its features will also translate with a proportional step size. Importantly, if we place a motion-compensated window around the features, then we see that the form of the translated features remains stable, independent of translation. This property arises by design from the translational weight-time structure of CNNs. If instead we consider input rotations, then we see that the motion-compensated features are not stable at all. Moreover, it is non-trivial to infer the relationship between two feature maps which differ only in rotation. Some have endowed CNNs with equivariance to discrete rotations by making use of multiple filter or feature map copies at those rotations. This works but does not offer full 360-degree equivariance, and computation scales with the number of rotations considered. Others have tackled the problem by averaging predictions over multiple rotated copies of the input, but again, this is only discrete and loses all local rotation information. Our solution is to replace regular CNN weights with a basis of circular harmonics, hence the name Harmonic Networks. Circular harmonics disentangle feature intensity information from 360-degree feature rotation, and they allow us to introduce equivariance to 360-degree rotation into the feature mapping. By passing both intensity and rotation between consecutive layers, we track how much of a particular feature is present along with its local rotation to build a very rich feature representation. Each circular harmonic picks off a different angular frequency in the input, allowing us to process each in a separate stream. At each layer, these streams are able to share information, allowing us to build very complicated rotationally equivariant deep features of far greater complexity than the circular harmonic alone. Returning to our motion-compensated view of the feature maps, we see that indeed harmonic networks are able to preserve deep features under rotation. Viewing the two motion-compensated windows side by side, the extra stability we are granted becomes apparent. We applied our harmonic networks to two tasks to test their benefits. The first task was classification on the rotated-MNIST dataset, consisting of 10,000 training images, 2,000 validation images, and 50,000 test images. Our 7-layer HNet sets the state-of-the-art on this problem, beating the previous state-of-the-art by 26%. HNets are also very data efficient. We reduced the number of training examples to just 2,000 images, seeing a drop in accuracy of 2.5% compared to competing CNNs, which dropped by over 11%. This is because regular CNNs require most of that data to learn to cope with rotations, which HNets take as a given. Our second task was boundary detection. State-of-the-art models rely on pre-trained networks, but we wanted to compare in the absence of transfer learning. We compared matched architectures on the Berkeley segmentation dataset 500, outperforming our competition while scratch training on just 5% of the model parameters. This shows that brute forcing a solution is not always the most effective means to an end. As a bonus, we can also extract edge orientation, which is color-coded. Thanks for watching.